In this lesson, we will be learning about how the electrons are arranged in atoms in the various energy levels. And to understand this, we need to be familiar with atomic number, which we have already seen in a previous lesson. Shells, again, this is something that we'll be using in this lesson, which we have learnt in the atomic structure lesson. The shells are also called as and referred to as energy levels very often. Groups and periods are descriptions about the rows and columns in the periodic table. Groups refer to the columns in the periodic table, top to bottom, the vertical lines, and the periods refer to the horizontal lines, the left to right rows, the rows and rows of elements. So that is the same as vertical columns, and the period is the horizontal rows. Move on to the next page to learn more about how the electrons are arranged in atoms, in different atoms and in different elements, and how this is connected to how the periodic table is organized, and in a way how it is then connected to their chemical properties. As we have already learned in atomic structure lesson, an atom can be represented in a simple way as shown here, and the central, the small part of the atom is where the protons and neutrons are found, and this is the mass of the atom is centered in here, and it's also called the nucleus. What's around the nucleus are what we call as shells, or the energy levels. First shell, second shell, third and the fourth shell. It is important to realize that these shells don't really exist. We draw that to represent the location of electrons, where the electrons are found at different levels. We should not think that they do exist as something physical. They don't physically exist. They are just imaginary pathways around which the electrons go around the nucleus. To proceed further, we need to know how to figure out the number of electrons present in an atom of an element from the periodic table. So I'm going to show that using a periodic table right now before I go and explain how the electrons are arranged in these shells. To figure out the electronic configuration, you need to be able to find the number of electrons in an atom. For instance, here we got potassium. All you have to look at is the atomic number, which is the smaller number of the two, and in this case it's 19. So that is its atomic number, or in other words, that is the number of electrons present in potassium. Now if you look at calcium, in a similar way, that number is the atomic number of calcium, which means that's the number of protons, which is exactly equal to the number of electrons present in calcium. We will need to be able to use a periodic table to figure out this, and the number of neutrons and protons from using the mass number. So that's the mass number, which is the number of neutrons and protons, and the atomic number gives you just the number of protons. So if you want to know the number of electrons, that is equal to the number of protons, because an atom is neutral, so the number of protons have to be equal to the number of electrons for an atom to be neutral, because protons are positive in charge and electrons have negative charge. So they must have equal in number for an atom to be neutral. So proton number is a small number, and that is the same as the electron number, and the number of neutrons can be obtained by subtracting 40 take away 20. So for the calcium, the number of neutrons will be 40 take away 20, that's 20. And in the case of potassium, the number of neutrons will be 39, take away 19, so that will be 20. We have already learnt about this in atomic structure lesson, so if you're not sure about any of this, you need to really go back to atomic structure lesson and go through that. We have just seen potassium's atomic number is 19, so I'm going to represent it, show it like that. And we also know that 19, that number, represents or shows how many protons potassium has got, and that is also referred to as atomic number. But we know, as potassium is a neutral atom, it should have 19 electrons. So what that means is the number of protons is 19 and the number of electrons is also 19. But primarily that number shows the number of protons. It's really important to understand and be able to say that if you're ever asked in an exam. The atomic number is the number of protons, but we know it is also equal to the number of electrons, and it's really important to realize that. Okay, now we're going to use this number to learn about how these electrons are arranged in an atom. What you see here is an atom but with no electrons on the shells. Now I'm going to start filling the shells using a particular rule called 2 8 8 2 rule, and this shows the order in which the electrons are filled in each of these shells. So what this means is, on the first shell you can only have a maximum of 2 electrons. On the second shell you can have a maximum of 8 electrons, and in the third shell 8, and in the last shell 2. For GCSE sciences, you only need to know how to write electronic configurations for up to an atomic number of 20. So here you go to 10 plus 10, 20. You do not need to write electronic arrangement or draw electronic arrangements for atoms whose atomic number is more than 20. So now let's have a look at how these 19 electrons of potassium are arranged in these shells. So in effect, I'm going to be drawing the atomic structure of potassium, how the electrons are arranged in a potassium atom. Electrons can be represented with dots like so, or crosses. Both are acceptable, but when we show in bonding we need to use these two different notations known as dot and cross diagrams. But for now, just for showing the electron arrangement in atoms, we can use either of this. Either of this is okay. So I'm going to be using crosses because it's easier to do crosses than dots. Okay, so for 19 I'm going to be adding 2 electrons on the first shell, and then I'm going to draw 8 on the second shell. Okay, like so. So now I've done 10 so far. Out of the 19, I have finished 10 electrons. 2 on the first shell. That's the maximum allowed on the first shell. On the second shell, I have put 8, and that's the maximum allowed on the second shell. Now I'm going on to the third shell. Again, I can do 8 because that will make into 18. So I can carry on doing the same thing. Another 8 here on the third shell. Okay, now that leaves me with just 1 electron left now, because potassium's atomic number is 19, which means it's got 19 electrons, and I have arranged the 19 electrons following that rule in that empty atomic shell, in the shells in different energy levels. So the first shell or the first energy level, I've got 2 electrons, 8 on the second energy level and 8 on the third energy level. Now so far I have used 18 of the 19 electrons of potassium. I've got 1 more to fill in now. I can put it pretty much anywhere on the last shell. I can put it here, and you may ask, why can't I put it here or here? You can put it anywhere on that outer shell. It's perfectly okay. Now I have shown the atomic structure of potassium with 19 electrons in a diagram like this. And you should be able to do similar diagrams for any atom up to an atomic number of 20. Before you go any further, let's have a closer look at this atom and the arrangement of electron. This shell, which is where you find the last electron, or the outermost shell, and it's referred to as the highest energy level that is occupied by the electrons of potassium. And the lowest energy level is here, where you find 2 electrons, second energy level, third energy level, and the fourth energy level. Sometimes also commonly referred to as shells: first shell, second shell, third shell, and the fourth shell. So potassium has 1 electron on the outer shell. We do need this idea when we learn about periodic table and the arrangement of groups. It is also useful to remember that the electrons are filled in from the lowest energy level to the highest energy level, from the innermost to the outermost shells. Let's have a look at another example. Aluminium. Its atomic number is 13, and in a similar way I'm going to be filling in these 13 electrons in these shells. So on the first shell I want to place 2 here, and then 8 on the second shell. Now I am just spacing out the electrons evenly. You can write these electrons in whichever manner you please. On the second shell you may want to place it anywhere evenly spaced out on the second shell. That's perfectly okay. But if you write your electrons like this, if you sketch your electrons like this, it makes it easier to count, and you can be in control of how many electrons you're adding in that way. If you draw it evenly spaced, or have some kind of control over your how you draw the electrons on the shells. Okay, now so far I have used up 10 out of the 13 electrons, so that leaves me with 3 more electrons. Now can I fill in the 3 electrons on this shell? That is where it has to go, because this shell is full. The first shell can have only a maximum of 2, if you remember using that rule. And on the second shell I have already used up 8 electrons. I can't add any more here, but I still have 3 more electrons left, so that must go on the third shell here. So I'm going to do just that. Now I can place them anywhere on the third shell. So I'm going to place 1 here, and 1 here, and 1 here, just evenly spaced out. Now I have an arrangement of aluminium like this: 2, 8, 3. Sometimes you may be required to write electronic arrangement in the number format like that, just showing how the electrons are arranged in the shells with just numbers like that. Okay, so that 2 represents the 2 electrons on the first shell, 8 shows how many electrons on the second shell, and the 3 shows how many electrons are on the third shell. You may even want to write like this before even you draw it on a shell diagram like this, because you can now plan to draw the atomic structure even before you put the electrons there, so you don't get this wrong. For example, if you have sodium with 11 electrons, you may want to write that as sodium with 11 electrons. Before you draw the structure, you may want to write in this format, so you plan your diagram so you don't get it wrong. For example, 2, 8, 1 for sodium. Now once I've done that, I know I've got 11 electrons, and if I added these numbers I should get 11, and I can now arrange these electrons on the shells. So I would put these 2 on the first shell and 8 on the second shell here, just like here. But on the third shell I will have only 1 left, so I'll have to put only 1 here. So this is a really useful way of first of all writing the number of electrons in each shell before even you draw the shell structure. This way you can't get it wrong. It is really important to have the skill of being able to write the electronic arrangement in this way to figure out the number of outer shell electrons. For example, in this case, for aluminium, it has 3 electrons on its outermost shell, whereas if you look at sodium, it's got 1 electron on its outer shell. If you've been following this and have understood how to draw electronic arrangement for atoms, you should now be able to draw similar electronic arrangement for beryllium, carbon, fluorine, sulfur and chlorine. Try this for yourself. Pause the video now and check back and play it again to see to check the answers. Time to check your answers. Beryllium has electronic arrangement like so, because its atomic number is 4. It has 4 electrons. The first shell will have 2 and the other 2 electrons will go here on the second shell. And similarly for carbon, as it has 6 electrons, I'm going to show the carbon's electronic structure now, which is going to be like so. As carbon has 6 electrons, this first 2 goes in the first shell and the next 4, the 4 that's left over now, will go on the second shell. So what you see now here is the electronic arrangement of carbon. It has 4 electrons on its outer shell. For carbon, please note that the second shell is its outer shell. You do not need to draw these 2 shells. So just the first 2 shells is sufficient. Now for fluorine's electronic arrangement, it has 9 electrons, so I should add here another one here, and now you got 9. The first 2 electrons are on the first shell, 7 electrons are on the second shell. So fluorine has 7 electrons on its outer shell. We do not need to draw these 2 shells, they are just empty shells. It is enough if we do 2 shells. If you draw 2 shells and show the electrons that are arranged like so. Now for sulfur's electronic arrangement. Now sulfur has an atomic number of 16, so it has 16 protons, which means it has 16 electrons. So how are they arranged in this same structure? So I'm going to add to the existing diagram, which I've drawn for fluorine. I just have to add the extra electrons now. It has 16, 2 is on the first shell, now 8 on the second shell, so I'm left with 6 more. Already 10 done here, 2, 8, so I'm left with 6 more, which I can draw over here on the third shell, like so. So 6 electrons here, and that is the structure of electronic arrangement for sulfur. So now please note that it has 6 electrons on its outer shell. So sulfur has 6 electrons on its outermost shell. Finally, let's have a look at chlorine's electronic arrangement. Now as you can see here, chlorine has 17 electrons. 2 is gone here on the first shell, 8 is gone, so 10 we have done so far. There are 6 already here, 1, 2, 3, 4, 5, 6, but chlorine has got only 17, so 2, 8, I need to put 7 on this third shell, so I just have to add the 1 electron anywhere on the third shell. I'm adding here, but you may want to add it anywhere. But if you want to spread the electrons evenly like so, it makes it easy to count. 2, 4, 6 and 7 electrons on the third shell. Here are the answers, but in a different format. What I have done here is just used the 2882 format to put the number of electrons in that order to see how the electrons are arranged in different shells. Now this is another way to represent electronic arrangement. As you can see here, beryllium has got 4 electrons. The first shell will have 2 and the second shell will have 2. Carbon is 6, 2 and 4. I'm just following that order. And fluorine similarly has 9 electrons, and that will be arranged 2 in the first shell and 7 in the second shell. Sulfur with 16 will go like this: 2, 8, 16. And the third shell will have a 6 electrons. And for chlorine it goes like this with 7 on its outer shell. So I have used different color to show the outer shell electrons, and this is significant. It is important in 2 ways. The periodic table of elements are arranged in groups, and that grouping is based on these outer shell electrons. It depends on how many electrons each element has on its outer shell. Second reason is that the chemical properties of each element, each group in fact, depends on how many outer shell electrons they have, because it's these electrons that take part in chemical reactions. Go to the next page to see how the electron arrangement and the periodic table are linked. First, let me give you a brief overview of how the periodic table is organized and the terms used to describe the periodic table. It has columns of elements, vertical columns of elements, and as you can see, these numbers here, 1, 2, 3, 4, 5, 6, these numbers refer to the group of elements. The middle group, this block here, is called the transition element block or transition elements. So we'll be concentrating mainly on these groups of elements and how the electronic arrangement plays a part in determining the chemical properties, and how they are classed based on, how they are grouped based on their electronic arrangement. You should also notice that it has rows of elements, and there is some significance to it. It has trends of properties from left to right as you go in a row, and these rows of elements are called periods. Elements in each group do have similar chemical properties. For example, in group 1 you have lithium, sodium, potassium and rubidium. Let me enlarge that for a minute. As you can see, in group 1 here you have lithium, sodium, potassium, rubidium. They all have similar chemical properties. The way in which they react with water and oxygen, and the products they make with the reactants, they are all similar. The only difference may be in the reactivity, how fast they react with these things, but they produce same products, and that it makes it very useful to group them, and it makes it so easy to study them as a group because they all have similar chemical properties. And as you look here, the second group, they do also have similar chemical properties over here, and so on. And then the transition metals have their own similarity in their properties. And then we have group 3 here, and then 4, 5 and so on. And finally we have a group of elements right at the end here. They are called as noble gases. These gases are very unreactive, and we will be learning about why some elements are very reactive, such as here. The first group of elements, the first group metals and the second group metals are comparatively very reactive compared to the noble gases, which is over here. So compared to the noble gases, and this group of elements react in a particular way. They all have very similar chemical properties called the halogens. So that's group 7. These elements are called halogens. They have very similar chemical properties. and they are very reactive compared to the noble gases. The noble gases are called so because of their unreactive nature, and all this reactivity is very much connected with the electronic arrangement, in particular how many electrons they have on the outer shell. So each of these group of elements do have similar chemical properties because they have the same number of outer shell, and this is the outer shell of electrons. This is what we're going to be looking at now a little bit closer. Notice that the group numbers are here: group 1, group 2, group 3, group 4, group 5, and this is really important to go into the next to see the connection between the electronic arrangement and the group numbers. The periods, the first period, the first row, it starts here with hydrogen. Sometimes in some periodic tables they put the hydrogen over here. It's perfectly okay as long as you remember hydrogen and helium, they belong to the period number 1. Okay, period 2 is the second period. Now, it is also important to understand the link between the electronic arrangement and this. For example, the elements belonging to the first period will have only one shell. Second period, 2 shells. Third period, 3 shells, and so on. Another important fact about periodic table is this line, the staircase line here. It goes right onto the left of boron and underneath boron, and it goes in a staircase fashion, and this separates the metals on the left hand side over here. All of these are metals. So there are many more metals compared to the number of non-metals that you have here. Non-metals are over here in this area. Now there are in-between elements as well, and you need to really understand how the periodic table is organized. Metals are on the left hand side, and then you have a group of elements in this area close to the staircase which are metalloids. They are in-betweens, so they're neither metals nor non-metals. There is a way of remembering where the metalloids are. If two edges are touching an element, then it's a metalloid. For example, this edge and that edge, I'm going to draw that and show what edges I mean. That edge and that edge is touching this element boron. So this makes boron a metalloid. And similarly, as you can see here, silicon is also touched by two edges of the staircase. So silicon is a metalloid. What about germanium on this side, Ge? Of course, that is touched by two edges of the staircase, so that is a metalloid. What about arsenic? That's a metalloid because two edges are touching. And antimony, Sb, is touched by the two edges of the staircase. What I mean by that is that edge there and this edge here. So these two edges are touching antimony and arsenic as well. So the arsenic is also a metalloid. And then I'm going to carry on to show all the edges so you can see that really clearly. So this makes us silicon a metalloid, boron a metalloid, germanium a metalloid because these two edges are touching it. Antimony is a metalloid, these two edges are touching it. Tellurium a metalloid, these two are touching it. And so polonium is also a metalloid, and what you have here, astatine, is a metalloid. The only exception to this rule is aluminium. Aluminium is a very common metal, so this rule does not, it's only a thumb rule, but this does not apply to aluminium, although this edge and that edge is touching aluminium in the periodic table. What I've done here is shaded the metalloids with the light yellow color over here, so you're able to see where the metalloids are. Remember, in summary, the periodic table is classed metals on the left hand side of the staircase. Close to the staircase line you have the metalloids, which are shaded in yellow, and on the right hand side you have the non-metals. Now we should be ready to understand how electronic arrangement, in particular the outer shell electrons, are connected to the groups the elements belong to. Let's pick sodium here with 11 electrons. So its arrangement would be like so. Sodium would be 2, 8, 1. As it has 11 electrons, the first shell will have 2 and the second shell will have 8. That's the maximum second shell can have, and the third shell has 1 electron. So that will be the arrangement of sodium. And if I pick another one, for example potassium here, which also belong to the group 1. They're all group 1 alkali metals. So I'm going to pick potassium with 19 electrons. And how would the electronic arrangement look like? 2, 8. So that's 10 done. And 18. And then, so you have 18 done, as potassium has got 19 electrons. And that 1 electron goes at the end. So if you count it again, 10 here, 18, 19. So that accounts for the 19 electrons of potassium. And this shows the first shell has 2 electrons, second shell 8, third 8, and the last shell, which is the outer shell for potassium, has 1 electron. And similarly, lithium has an electronic arrangement of 2, 1, as it has 3 electrons in total. So first shell has 2 and the second shell has got 1 electron. You must be able to notice some pattern here with respect to the outer shell electron. I'm going to underline this here. As you can see, all these elements have 1 electron on their outer shell. This is why they have very similar chemical properties. They react with these outer shell electron, which means they react in a particular way. By losing this electron, we'll see this in how these elements react together in the following lesson. But for now, what we should understand is the chemical properties depend on these outer shell electrons, and because they have the same outer shell electron, the chemical properties are very similar. You pick any other group of elements and they show similar trend. So I'm going to now show the similar trend repeating for second group number 2, and maybe for group number 3, and one from group number 4. What you will notice is each group has the outer shell electron, which is the same as the group number. So if all the elements, all the metals that belong to group number 1 will have 1 electron on its outer shell. So let's pick something from group number 2, say for example that magnesium with 12 electrons. So magnesium can be written as, magnesium's electronic arrangement looks like so, 2, 8, 2. And for calcium, which belong to the same group 2, it's a group 2 metal, and it has electronic arrangement 2, 8, 8, 2. As you can notice, as you can easily see, the outer shell electron, the number of outer shell electrons is 2 in each case, as they belong to group 2, and that is why they are placed in group 2, because their chemical properties are very similar, and that depends on their outer shell electron. In other words, you can say they have very similar chemical properties because they have the same number of outer shell electrons. So if you pick another one here, now you do not need to know the atomic structure or the electronic arrangement for strontium, but you can say that it will have 5 shells and it will have 2 electrons on its outer shell. Here I have shown 3 elements, 3 metals that belong to group 2. Beryllium is here, and magnesium, that's next, and then calcium. Calcium's electronic arrangement is also shown here. You cannot miss that they all have 2 electrons on their outer shell, and that's why they belong to group 2, and that's why they have similar chemical properties. It's also important to also notice that beryllium, which belong to second period, has 2 shells, 1, 2. First shell has 2 electrons, second shell has 2 electrons. Magnesium belongs to period 3 or third period, so it has 3 shells, 1, 2, 3. Calcium belongs to fourth period, so it has to have 4 shells, 1, 2, 3, 4. and because it belongs to group number 2, it has 2 electrons on its outer shell. Similarly, you can try out the electronic arrangement for boron and aluminum, carbon, silicon, any of these atoms, any of these elements, and you will notice that the group number will be their outer shell electron. I'm going to show one more just to finish this off. Let's have a look at chlorine, which has 17 electrons. So chlorine will have electronic arrangement like this: 2, 8, 7. As you can see, there are 7 electrons on its outer shell, and its group number is 7, which you see here. You can try out fluorine. You will notice it has 7 electrons on its outer shell, and so on. Bromine, you do not need to be able to write electronic arrangement like this because it's slightly more complicated, and you at GCSE level you're not required to know more than 20, which is up to calcium you need to be able to write. So bromine is more than that, but you can say as it belongs to group 7, you can expect bromine to have 7 electrons on its outer shell, and it will have similar chemical properties. It will react in a similar way to chlorine and fluorine, as they're all halogens and they're all group 7. Another very important thing to know and understand is that the noble gases have very similar electronic arrangement. They are called either group 8 or 0. As you can say, the outermost shell has 8 electrons except for helium. As we can see here, helium has got only 2 electrons, so its electronic arrangement is 2, which makes the first shell complete, its full outer shell. For neon, its electronic arrangement is 2, 8. As you can see here, 8 electrons on its outer shell. That makes the second shell full, and its complete outer shell for neon as well. For argon, it's the same case. It has 8 electrons on its outer shell. So all these noble gas elements, they have full outer shell, which makes them very stable, and this is why they are very unreactive. So if you're ever asked why noble gases are very unreactive, you should be able to say they have very stable electronic arrangement. So stable electronic arrangement, and you should be able to say they have full outer shell of electrons. So these 2 points are really important for noble gases. Move on to the next page to summarize all this information. Time to check your progress and understanding so far. You can reflect on these questions. You may want to write this down on a piece of paper. Pause this video now, come back to the video and play to hear my answers. Now for the answers. Can you explain the connection between the number of outer shell electrons of elements and the group they belong to? As you know from the previous page, that the group number is the number of outer shell electron. In other words, the number of outer shell electrons is the group number of that element. For example, aluminium has 3 electrons on its outer shell, and so it belongs to group 3. The second question, an element has electronic arrangement of 2, 8, 6. Just have a look at the outer shell electron, which in this case is 6. So this is an element which belongs to group number 6. You can actually find what element it is by looking in the periodic table for an element or an atom with atomic number 16, because 2 plus 8 is 10 plus 6 is 16. So if you look for an atom with 16 atomic number, you can find exactly what element that is and check if it belongs to group 6. Question number 3, can you explain why groups of elements have similar chemical properties? They do have similar chemical properties because each group of elements have same number of outer shell electrons. Explain why noble gases are very unreactive. And this is because noble gases have full outer shell and they have a very stable electronic arrangement because of that. So they are very unreactive.